The fact that they're heavy just means that they don't blow up.
Right.
But they still chirp their energy.
Yeah, but the space charge, I thought it's...
The space charge is the thing that's causing their energy to chirp, not their size to blow up.
Gotcha.
Right. The fact that they're stiff is great, because it means they'll stay microbunched even as they get chirped.
Okay.
Right? So, this is really a cool idea. That was wrong to genius. All right, I'm done. Strong field, laser fields can induce impulsive dynamics. Okay, go away from this talk thinking impulsive excitation. It's what we do in order to get science out of the experiments that we can match up to real calculations and make progress in this field. Tools now exist to extract spatial and temporal information about electronic motion, about nuclear motion in molecules on these timescales, and we're getting into this attosecond regime. And X-ray FELs are going to have, I think, a really important role in this in the future. And I'm done. I've had a tremendous amount of fun here. You know, the weather was better the other time I came to this school, so maybe I had a little more fun then, but, you know, other than that, here's my group again. I showed them at the beginning, I'm showing at the end, because they are actually responsible for much of what, well, everything that we actually accomplish, and a lot of what we think about. And that's the tip of the iceberg, because so many collaborations, of course all of the experimental groups are like this. Here are just a few alumni and collaborators. Okay. And finally, thanks very much for a wonderful week.
So remember, your last chances for questions. Yes.
Assuming that you know the molecular structure beforehand, is there an upper limit to the complexity of molecules you can use this technique on?
No. That's a reasonable question, but I'm pretty sure the answer is no. And just to give you an example, it's not really in the impulse limit yet, but to give you an example of how things could go. People have used pump probe methods to detect the motion of retinol in bacteriorhodopsin. And that's a big molecule with a little tiny thing in it that's moving, and I still were able to do it. Now, you know, special case in many ways, but nonetheless, it demonstrates this principle that even in highly complex systems, you can get really useful information. And I think the reason for that is because as long as you want to confine yourself to short time scales, you can simplify even these very complex problems. I mean, you know, the kind of problem you can't deal with in this way is something like protein folding. That's a big problem, very important problem. It's not a pump probe problem. It's something that just doesn't, there's just no way to get in there and do some kind of impulsive thing for protein folding. But for things like chemical reactions, you know, which are initiated, or catalysis, things that are initiated by getting over an activation barrier, and then everything happens. This is great. This is exactly the kind of problem you can solve.
For the free electron laser, and the spectrum will be a little bit random, so is it available to the component control in the experiment?
Yeah, it's a really good question. In Girard's example, the bandwidth that he's seeing in this example at the very end, where he showed that you could make 200 attosecond pulses from the longitudinal space charge in the microbunch. That was something where the energy should actually be rather stable with respect to the center of the bandwidth of that pulse. And the reason for that is because that's a lot of bandwidth. In cases where you have longer and therefore narrower bandwidth femtosecond pulses, there's a lot of energy jitter that's much greater than the full width half max energy of a single pulse. And then you have problems with control that you have to deal with some other way. One of the ways that you couldn't deal with those problems even there is with external conditioning of the electron beam with a laser. I showed a little bit of that in my second lecture. I have one slide on it here too, where upstream you create an artificial density modulation in your electron beam that has a modulation wavelength that you chose. And you can actually control things better that way. Another way that it has been controlled at LCLS and is available for users now is through something called self-seeding. So Linda talked about self-seeding quite a lot, where you get a little lasing happening. You don't really know, it's got a lot of jitter and energy. But then send it through a monochromator, either a crystal or a real grading monochromator. Filter out the part that's at the energy you want and make that be the seed for the rest of the free electron laser. Then that works too.
On this attosecond pulse, does the dispersion or the dispersion compensation happen for free as well, or do you have to actively put these different energies back together in the light?
It's a second. Yeah, once it's in light, you can't play these games with magnet-based dispersion compensation. You have to use light-based dispersion compensation. Of course, we know how to do that. We knew how to do that first. It doesn't mean it's easy, but you'll have to worry about the second-order phase separately from this. Now, I should point out that although I hesitate to call it impulsive, that stimulated Raman is independent of whether your beam is chirped or it's not chirped. Sort of an interesting thing. Well, it's not 100% true, actually. Depends on how far apart the Stokes and anti-Stokes line are. They could be so far apart that if you chirp the beam, you kind of lose it and it doesn't work. But generally speaking, because it only is concerned with pairs of photons, rather than the actual color of any one photon, some amount of chirp doesn't hurt you. It doesn't hurt you as fast as you might expect it would, just simply based on the full width half max getting bigger.
Other questions?
I have a stupid question.
I was going to ask one.
So I'm first. So I'm a two-state system guy, okay?
Yeah.
Sometimes I've done three, but it's kind of pushing my luck. Out of the gazillion of molecules which are available, how do you pick one rather than the other to do specific type of experiment?
Well, there's not one answer to that. If we're trying to do an experiment in the molecular frame, then we try hard to pick a very small molecule that we know how to impulsively align or at least get into some coherent motion. And then everything that we do will have to work for that, okay? If we're interested in making use of the range of soft X-ray wavelengths that are available at LCLS, see, this is really an important example of what you just said. There have been probably 100 experiments on LCLS on oxygen and nitrogen, and hardly any on sulfur. Why? Well, what colors can the laser produce? We say, oh, it's completely tunable from the carbon K edge at 300 eV all the way up to 12 kilovolts. It's completely tunable, but there are actually some regions where it almost pretty much can't get to because of the optics that are downstream. And 2 kilovolts, between 2 and 5 kilovolts is a really difficult region. And so it's a really important region for chemistry, by the way. So that really important region for chemistry is something that we just can't reach. And so we never do experiments that involve those kinds of atoms. LCLS2 will fill in the gap, which is very important.
So I have one question regarding this very beautiful experiment on the stimulated impulsive Raman. And so I'm only thinking in theory. I can also do it with the CW, 2-photon, 2-color CW lasers, and the matrix elements are the same. So what is the take-home message here? What is you gain in the yield of the photons? What?
Yeah, the take-home message is that what the high intensity buys you is that the rate of the 2-photon process will then become higher than the rate for the 1-photon process that forms your main background.
But
So-
compared to the CW Raman, the stimulated Raman.
But in CW stimulated Raman, you would not have a very high intensity.
That's right.
And therefore, the linear processes, like ionization, would be exactly the same as here, but the quadratic process, the stimulated Raman, would be much weaker. The cross-section is the same, but the fluence is down, or the intensity is down. It goes like the intensity squared. I mean, I think in terms of fluence, because I'm always interested in yield, right? But if you can think in terms of rate, so it's not fluence, it's intensity. And the fact that the intensity is down is going to mean that the linear process will not be adversely affected, but the quadratic process will. Yeah.
Very good. Any other questions? Remember, your last chance. Going once,
Okay.
going twice. Oh.
So where do you see the field in 10 years?
Oh, I think in 10 years we'll have a lot of attosecond sources in the free electron laser community. Fermi, Swissfeld, possibly even, by 10 years from now, possibly even in Sweden. And of course, we'll have Flash and LCLS2. And that's enough to drive a very robust community. And we'll certainly be able to explore this attosecond range, this charge migration problem. In fact, the charge migration problem there may be some new paradigm. As there was, for example, in BEC. When BEC first got started, we didn't even realize that it would actually shift the question of what's interesting science. So now you study different things, right? I think this has the capability of doing that as well.
Yeah, I think this charge transfer is hard not to crack. I think this would be Yep, one more.
Do you have any reasons why don't you use seeding in LCS2?
Do I have any reason to do what with LCS?
I heard that you don't in LCS2.
Yeah.
You're not going to implement seeding process.
I'm not going to
Seeding.
we're not going to seed. Oh, I hope they do seed. It's a lot of my campaign is to get that into the baseline of the project. There is some wiggle room in the baseline of the project right now, and they're not going to do HGHE seeding because that's too hard to get up to that. And that works at Fermi, but that won't work well if you're trying to get to say 3 kilovolts. But other things, these echo type schemes where you place modulations on the electron momentum by having it co-propagate with a laser beam. Those schemes will almost surely work. And my allies in this are all of the accelerator theorists, the FEL theorists, who just love this stuff. And I think together the AMO community and the FEL theory community will make sure that this happens at LCLS2. It's an ideal place. We've got the real estate. It hasn't been designated for any funding to do anything with, and this is what we're working on over the next few years. That's sort of a political impediment. It's not a physics problem.
If there are no other questions, then I suggest you join me in thanking Professor Bucksbaum for So we'll take a few minute break. We have time. And we will come back for the very last lecture.